Welcome to another beautiful talk by Emilio on Thomason style model structures on simplicial complexes and graphs. Take it away.
Mike Snowson. Okay, so recently I've gotten interested in what's called graph homotopy theory. And this is the idea of using homotopy theory to study graphs. Okay, so start off with a theorem of Kapulkin-Carranza from a couple of years ago. It says there are exactly two symmetric monoidal closed products on GR. Okay, so what's GR? GR is a category of graphs.
Which one?
Unfortunately, it's not the same category of graphs I talked about last time.
You talked about 8 of them.
Yeah, so
right over there.
So now this is the category of reflexive, undirected graphs. So what do I mean by that? I mean two things.
With and without self-loops.
So I can think of them in two ways. One way is I think that they all have loops, all of the vertices, and there's at most one loop. There's exactly one loop on every vertex, and there's at most one edge between any two vertices. And so I can map this into here. I can crush this down to a point. Okay, so morphisms, I can crush this edge down to this point, and you imagine there's all loops. You could also just erase the loops, which is what I like to do.
Is that a pre-sheaf category?
It is not a pre-sheaf category.
You don't have a word to say that. Reflexive means it has little loops, and undirected means it doesn't have arrows. But you don't have a word to say that isotropic thing that you just said, that namely between any two things there's one thing.
Simple. Because I know exactly what it is. It's the concrete pre-sheaves on a category. Okay?
And we have no idea what the word concrete means.
Okay, give me a sec. All right, so this is the category I'm talking about. You can just think of it as simple undirected graphs, and I'm allowed to crush edges down to points. Okay? So this is the category I want to work on. It turns out there are exactly two symmetric monoidal closed products on this category. Okay? So what are the products? There is the categorical product. And if you take this graph and you multiply it with this graph, you get this graph, which is a complete graph on 4 vertices. And then there's another one called the Cartesian product, also called the box product. And there, if I take 2 intervals and multiply them, I get a square. And these are both closed, which means...
Is there an easier way to say what that box product is in general for any two graphs?
Yeah.
One second. The other product also needs a nice definition.
Yeah. Have an edge between them. If I have at least one edge, x prime, x prime, or y prime, or between them if one of the entries is equal and then there's an edge in the other one. Okay, so these are the two products and they are closed, which means that this functor and this functor have right adjoints. Okay, and this is very useful for homotopy theory. And what we're going to focus on today is the categorical product. So each one of these products give you a different notion of homotopy theory for graphs. So how?
This might be a computer side, and so you can work for later, but so you know how come these are the only two, or is that just a...
That's a theorem.
You know,
They're exactly...
I know that, but the theorem's, it's only theorem because I'm proof, so I just wanted to know why.
Oh, why? Like, what's the proof?
If there's an easy thing that can be said about it, if not, don't worry.
Well, they use the fact that this category, GR, as I said, I didn't explain yet about it being concrete presheaves, but they use that. Because you can study the products on the presheaf category, and then they use that. Okay? Okay. So, right, okay, so I have this, and then if I want a notion of homotopy, then suppose I have F and G are two maps of graphs, right? And these can be infinite graphs, but I have two maps. I want a homotopy between them. That's a map like this, where IN is just the interval graph. Okay, so I have, let's say, 0, 1, 2, 3, 4. This is I4. Okay, so it has 4 edges. So that means I have a notion of homotopy for every n. Okay? So, say they're homotopic if there's a homotopy for some n.
This is your stuff already, or is this?
No. None of this is my stuff. So I could replace this categorical product with the box product, and this would give you two different notions of homotopy theory. Okay? But for this talk, we're going to stick with this product. And it turns out that actually both products have already been studied in combinatorics for some time now. Okay? But in totally different contexts, and they didn't really know that they were working with some kind of homotopy theory. So let me start with the categorical product. Where does that show up in combinatorics? So in combinatorics, Lovash proved something called the Neeser conjecture, which was to find the chromatic number of a certain kind of graph. So find the chromatic number of what's called the Neeser graphs. Okay, and the way he did this was by proving, so this is the chromatic number of a graph, that if you take a graph, its chromatic number is bounded from below by the connectivity of a certain space. What is that space? So first of all, this space right here is G, this graph right here, G to the upper K2. What is K2? So Kn is the complete graph on n vertices. So I have K1 is a point, K2 is an interval.
I1. So K2 equals I1.
K2 equals I1. K3 is a triangle. K4 is a tetrahedron, and so on. Okay? Now remember, I had a closed monoidal structure, which means I had an internal HOM. So G to the K2 is the same thing as HOM K2 into G. Right? So this is a graph. I want to get space out of it. That's what this CL does. So CL, which we're going to talk about more, is called the clique complex functor. It takes a graph to a simplicial complex. What does it do? It says every time I have a graph and I see a complete subgraph, I fill it in. Now I have a simplicial complex. Now I can look at its connectivity. What's the highest homotopy group that's non-zero?
Oh, that's what you mean by connectivity.
That's what I mean by connectivity. This number is bounded below by this. Okay? So this was proved in the 70s. And of course, he didn't use any idea of like homotopy theory internal to graphs. He just took this space and he did homotopy theory, used the Borsuk-Ulam theorem, and he was able to prove it. Long-standing conjecture.
So no functor.
No functor. He didn't think of it as a functor, but it is a functor. It is a functor, though.
Yes, I agree.
Okay. So from there, people got really interested.
And is there an intuition here?
It's not so easy. You shouldn't have any intuition why this is true.
Okay, good. I don't.
So this could have, that by itself could have been easily another talk.
Absolutely, absolutely. So this is a true statement, though. Okay.
In other words, the chromatic number doesn't seem to have anything to do with functions. Basically.
No.
Okay, but I do want to say that they're doing now chromatic numbers using sheafification sheaves and stuff like that. Okay, right. That's good.
Right. Okay, so this is the Lovaas's proof, and it ushered in an era of topology coming into combinatorics. Okay, so people built on this over the years, and then in the 2000s, Doctorman introduced X-homotopy theory, which is just the idea that I told you about before, that you have these homotopies with the X, the categorical product. Okay? Right. Okay. All right, so I got interested in this and I wanted to understand this X-homotopy theory, and I read a paper of Matsushita. And in that paper, he constructs a model structure on the category of loop graphs. So here's another category of graphs, okay? So loop graphs are graphs that can have at most one loop and are undirected. Okay? So for us, reflexive graphs, every vertex has a loop. And now I'm not allowed to squash an edge if there's no loop there. So for instance, I could squash this edge here, but I couldn't squash this edge to there. Right? So this is a different category. Okay? But he constructs a model structure here, and he did it in a little bit of a surprising way. So the first thing he considers is a functor to simplicial sets. Call that sing. What does sing do? So sing takes a graph and gives a simplicial set which in dimension n maps in complete graphs. And I'm thinking of these as unlooped complete graphs. Okay? So you map these things in and you get a simplicial set. Okay? And this has a left adjoint, which I'll call realization.
So you allow degenerate ones where they could collapse with this thing, right?
Oh yes, I'm sorry. These are looped. These are reflexive complete graphs.
Yeah.
Otherwise it couldn't be a simplicial, then you couldn't have degeneracies. Right? So these are looped complete graphs. So if this thing has no loops, there's no maps into it. Okay, so that's the first kind of weird thing you're seeing here. Yeah, you can't map something that has loops into something that doesn't. Okay, can't do that.
So this is just mapping circles into the graph.
Circles, these are complete graphs. These are these guys, they're like simplices.
Yeah, okay.
But for graphs.
Tiny circle.
But they're not cycles, they're simplices, right? So I map these in. All right, but this, and then you get this adjunction, this is not what he uses to construct a model structure, though. Okay? Instead, what he does is this. He applies subdivision twice and then realizes it. And then here's the right adjoint to subdivision. So that's kind of a weird thing. And I thought about where...
Is cons x thingy?
That's cons x functor, yeah.
Tell us what x does.
No. You just map in, instead of mapping in simplices, you map in subdivided simplices.
So you're going to take the model category strip that's induced. Simplicial sets have model category structures, and you're just going to induce what your weak equivalences are and your vibrations and equal vibrations.
Exactly. So Matsushita,
I assume it didn't work before. That's why
it doesn't work. It didn't work before. You have to add in the second subdivision. Okay. So where I asked myself, where had I seen that before? And I had seen it before in the Thomason model structure. So what's the Thomason model structure? I take categories and I take the nerve functor. The nerve functor has a left adjoint called the homotopy category functor. So we know what the nerve functor is. The homotopy category takes a simplicial set and makes a category where the objects are the vertices, and the morphisms are homotopy, are the one simplices, and then you mod out by two cells, by two simplices, okay? So this is an adjunction, But again, Thomason doesn't transfer the model structure through this. Okay? He has to subdivide twice. So the basic idea is this kind of incredible fact. If X is a simplicial set, then the co-unit is not a weak equivalence in general. Because you can imagine, you take a big simplicial set and you crush it down using this homotopy category construction, and then you take the nerve of that thing. You've lost information, right? This is not a weak equivalence. But if I take the subdivision twice, this is a weak equivalence. So the idea is somehow subdividing twice remembers, and then taking the homotopy category, it remembers enough of the structure of X to get a weak equivalence. Okay? And this was proven independently by Thomason and Fritsch-Latch in the early 80s. Okay?
Latch was a student of Heller.
Didn't know that. Nice. So then Thomason uses this idea to transfer the model structure from simplicial sets onto categories. And he's able, using this fact, to show that it's equivalent equivalence. Okay? So what are the weak equivalences here? These are functors such that this is a weak equivalence of simplicial sets. And what are the fibrations? They're the things that when I apply this functor, I get a fibration. It's not at all obvious what that actually means, though.
Say weak equivalence of simplicial sets, that's the same idea as for spaces?
Yeah. Yeah, so if you take a simplicial set, you can geometrically realize it. So I have a map of simplicial sets, that's a weak equivalence. If on the geometric realizations, it's a weak equivalence. Okay? Because if this thing is a weak equivalence, then just this is. So that's why I wrote it like that. Okay, so Thomason did this in the early 80s, and he constructed a model structure on categories called the Thomason model structure. Okay? Now the Thomason model structure is kind of funny.
He had another model structure on that.
What's that? I'm not sure that's due to Thomason, though. Yeah, folklore. So there's another model structure on categories where the weak equivalences are equivalences of categories. But these are not the same model structure. And they're not equivalent. Okay, so the Thomason model structure is a little bit odd in the following sense. We have a pretty good understanding of homotopy colimits and homotopy fibers in the Thomason model structure. And that's pretty rare. It's not often that you can just kind of produce homotopy colimits and homotopy fibers relatively easily. So these were due to Thomason and Quillen. And here what I'm referencing is often called Quillen's theorem B, or Quillen's theorem A and B. Okay? And then Thomason gave a formula basically for the homotopy colimit of any diagram of categories. Okay? So what do you do if you have a diagram of categories? You can take the growth and deconstruction. This is the homotopy colimit of F in the Thomason model structure, right? Because it's a category. Okay, so let me not harp on that too much, but there's a disadvantage. We don't know what all the fibrin and cofibrin objects are. It is still an open problem to this day to come up with a clean characterization of the fibrin and cofibrin objects in the Thomason model structure. We know some things. Thomason proved that all the cofibrin categories are posets, and then there's been partial progress since then of obtaining when categories are fibrin or cofibrin, but we have no complete understanding of them. So this is kind of in reverse to most model categories, where it's typically pretty easy to figure out what the fibrin and cofibrin objects are. It's hard to compute homotopy limits and colimits. Okay?
Before you reach the part of the second ST2, does it have anything to do with something like that in homology del 2 is equal to 0?
Not really. No. Yeah, I didn't either. So, but it'll become clear, I think, as I explain this, like where this becomes important, at least in the context of what I'm doing. Okay, so this is a Thomason model structure on categories. And so I read Matsushida's paper, and I realized that he's just doing the same thing. He didn't say anything about Thomason in his paper, but it's, you know, if you look at the two papers, you compare how they're proved, it's very, very striking similarities.
A category is a graph, it's just one where you get to multiply the edges.
Yeah. Okay, so what do I do in my paper? I factor Matsushida's construction. So Matsushita had an adjunction from loop graphs to simplicial sets, and I factor that through 3 adjunctions. So I have to explain what these all mean. Okay, so this is the category of simplicial sets. This is the category of simplicial complexes. I'll define what that is in a second. This is reflexive graphs, and this is loop graphs. If you go all the way here, this is Matsushida's thing. If you go all the way here, that's the left adjoint. Okay, and I take the Quillen model structure here and I transfer it all the way along. I obtain model structures here and here, and all of them are Quillen equivalences. And it's exactly Matsushida's construction there.
Are the first 2 pairs of arrows also adjunctions? Or?
These are all adjunctions.
Okay.
Okay. All right.
The I over there just includes in reflexivity?
Yeah, so you imagine you have reflexive graphs are just loop graphs where every vertex has a loop. So I can just include it into here. And then this takes the maximal reflexive subgraph. So if I have no loops, it just sends it to the empty graph. Okay. Okay.
And everything else gets crushed to zero, to the points. You have no, so if you have loops, if you have
If they don't have
loops,
loops, they go away.
and if they don't have loops, they go away.
Exactly.
And the next one, we're not gonna even try to figure out CL versus.
This?
CL, you talked about, you wrote CL.
Oh, this is the clique complex functor that I talked about. I'll explain it again. This takes a simplicial complex, and it just takes its one skeleton. Takes the underlying graph. Okay? All right. Maybe I should rewrite this over here so you guys can stare at it.
Now, on the map sound familiar, remind me what was so the original goal was just to find a map that went all the way across there in the junction, or?
Matsushita's construction is the composite of all the adjunctions.
Okay.
So I factor his construction and I transfer the model structure all the way across. So I gain two new model structures.
And now you probably gonna try your other definitions of graphs, and some of them, it's not gonna work.
We really need it to be reflexive graphs.
Sure.
When you do it with loop graphs, you're passing through this maximal reflexive subgraph anyway. So what Matsushita is doing is he's taking the model structure from here. He doesn't see the unlooped part at all. Okay? And that's because you can't get a simplicial object here, because you can't crush things.
Well, this went back to when you were showing how you map the simplest, and you were saying that, you need the loops for it to map in.
Exactly. Exactly. Okay, so now I'm going to give the definition of a simplicial complex. Simplicial complex K consists of a set V of K and a collection, which I also call K, of subsets such that if tau is in K and sigma is a subset of tau, then sigma is in K as well.
So this is the old-fashioned.
This is the old-fashioned abstract simplicial complexes. So for example, V of K, A, B, C, and D A, B, C, D, then what are the simplices? If I color this in, then K consists of, I'm not going to do brackets here, so I'll just say ABC. That's this simplex. That's the subset ABC. And then I have to have every subset also belong to it. So that means I have AB, BC, AC, and then I also have CD, A, B, C, and D. These are all the simplices, right? And now a morphism of simplicial complexes is a function that takes simplices to simplices. And again, I'm allowed to crush simplices.
So CW complex is a little different.
CW complex is definitely different.
There's some complexes.
And I call the category of simplicial complexes complex. Okay? So simplicial complexes show up more in combinatorics than they do in homotopy theory. They have a lot of disadvantages. So disadvantages for homotopy theory. You can't do something like a loop, right? Because I can only have edges between two different elements, right?
Well, you're always having to subdivide things.
You always have to subdivide things. Whereas here, this is a perfectly good simplicial set.
And a perfectly good CW.
And CW complexes. So simplicial sets are used in homotopy theory. They're more convenient. Simplicial complexes have kind of fallen by the wayside in homotopy theory, but in combinatorics, they're used all the time. So much more popular in combinatorics. And they're far simpler than simplicial sets. Sorry?
Just as offhand remark. They haven't been subsumed like that.
Yeah. We also have ordered simplicial complexes. So if I have a simplicial set, the face maps give me a total ordering on all of the simplices, right? Simplicial complexes have no ordering on them at all. Ordered simplicial complexes are something in between, okay? An ordered simplicial complex is a simplicial complex K along with an ordering on the set of vertices
It's a total order.
such that
Or
every simplex is totally ordered. So the whole set doesn't have to be totally ordered, but when I restrict to any simplex, it does have to be totally ordered. Okay? Okay. This gives me another category. Funnily enough, very soon after I put my paper on the archive, another paper came out putting a model structure on ordered simplicial complexes. So all of this stuff is in the air, okay, and it uses it's very similar subdivision, all of that stuff. Okay.
So only now someone can put a model structure on ordered simplicial complexes?
Somebody already did. That's what I'm saying, right after my
No, but
paper.
I'm saying that so many years after model structures and.
Right. Only now.
That's what I'm saying.
Yeah, only now is it becoming kind of more popular. All right, so ordered simplicial complexes. But, all right, so.
Is there a requirement on them, I'm sorry, such that is there,
And morphisms have to respect the ordering.
oh. In other words, if x is less than y, then f of x will be less than f of y.
Yes.
It's collapse.
Yes. Yes. It's a poset on the set of vertices. Morphisms have to respect that ordering.
Is that a free-shoot category?
No. Okay. So I have ordered simplicial complexes, and now I have a functor, so I call this O complex. And I have a functor from this to simplicial sets, which I'm going to call O sing. And it's going to be the obvious thing. O sing of an ordered complex, I'm going to call it K less than or equal to. So this is an ordered simplicial complex. Now I take ordered complex maps from delta n, thought of with its canonical ordering, into my ordered simplicial complex. I'm not allowed to map this thing in however I want. It has to respect the ordering. Okay?
That's a very rigid category until you make complicated. That's shocking.
So I get a simplicial set. What is the simplicial set? It's just think of it as a simplicial set. Give it freely its degeneracies. It does almost nothing, right? So I have this ordered simplicial complex. I think of it as a simplicial set. This functor turns out to be fully faithful. And the image, the essential image of this functor has been studied for a long time inside of simplicial sets. So Peter May calls simplicial sets in the image, where he says simplicial sets in the image satisfy properties B and C. Okay. Doesn't matter a whole lot what that means. I'm just saying he has another name for these things, those that satisfy B and C.
There's another thing called a Kahn complex.
That's not relevant here.
It's not related.
Won't that go the other way?
Yeah.
Won't that go the other way?
Yeah, there's a left adjoint.
It was relevant last week.
Yeah, last week was on.
Okay, so we have simplicial complexes, ordered simplicial complexes, simplicial sets. Okay. Now, I can always put an ordering on a simplicial complex and get an ordered simplicial complex, but it's not functorial. There's no functor from complexes to ordered simplicial complexes. Of course, there's a forgetful functor, though, right? No, there's no canonical way to assign the ordering. Okay. I should also remark that lots of simplicial sets that we care about are in the image of this functor, like delta n, horns, partial delta n. Being in the image of this functor is going to be really helpful in a minute. Now, we also have a functor just from simplicial complexes into simplicial sets. And what does that do? It takes a simplicial complex, gives a simplicial set given by just complex maps from delta n, and I'm going to underline it to think of it as a simplicial complex rather than a simplicial set, into K. Now there's no ordering. So if I ever have a map of a simplex into my simplicial complex, I can permute it however I want. That's another map. So this thing's huge. Okay? This simplicial complex has three simplices. Right? And then for every two simplex, it has that. Okay? So it has tons and tons of simplices. But there's an amazing fact. Camarina proved in a blog post that if I take an ordered simplicial complex and I take osing, so remember that was the small simplicial set that I got because I just order it. So there's only one simplex in the simplicial set, right? Because I have an ordering. And then I map this into Sing of the underlying simplicial complex. This map is a weak equivalence. Okay, so you have an ordered simplicial complex, you can just forget about the ordering, take Sing, is this big thing, or you can take the smaller one, they're weak equivalent. Okay, so that's a really nice fact. How much time do I have?
It's 5 to 8.
5 to 8. Maybe I'll skip the proof.
Which model structures?
This is just simplicial sets.
Okay.
So in the Quillen model structure on simplicial sets. Okay, so let me try and skip some stuff. Let's see, how much longer should we go for? 15 minutes?
What are something you wouldn't want to get to?
I don't know. I have like a ton of stuff here, but let's just keep going and see what we get to until we get tired. All right, so let's talk about subdivision. So I want a subdivision functor on simplicial complexes. So the first thing I do is I come up with a functor from complexes to posets. I call this the face poset. Okay, so if I have a simplicial complex, I can get a poset out of it, where each of the faces, or simplices, faces, simplices are the same thing, becomes an element of the poset. A, B, C, A, B, A, C, B, C. A, B, C. Okay. All right.
Looks like you recovered it.
Right. And then I have a functor the other way, the order complex of a poset. And here, if I have a poset, let's see, which one did I use here? Let's do a different one. And every chain in this becomes a vertex in the complex. Okay? So I'd have something like A, B, wait, what am I saying? Oh, I'm sorry. No, I get a complex where all of the elements are vertices, and then I make them a simplex if there's a chain. Right, so here's a chain A, B, C. Here's a chain B, D, like that. And here's a chain B, C, D. Right? So you get that. Okay, so the subdivision functor is the composition of these two. Okay, so what does it look like?
It looks up to be old-fashioned barycentric subdivision.
This is old-fashioned barycentric subdivision. So I have ABC, I get its face poset. Right, A, B, C, AB, AC, BC, ABC, all right? And then when I take the order complex of that, it's gonna
Oh, I see. Okay.
look like this.
Clever.
Yeah. Took me a moment to see how it works.
So I have A, AB, B, BC, B, and ABC,
Okay.
right? And then each of these gets filled in. So that's subdivision for simplicial complexes. And you have to do it twice. You can also subdivide a simplicial set, right? So if I have a simplicial set, I take the colimit over all of its simplices, and I subdivide that in this way. And I think of that as a simplicial set. I take the colimit. Okay, so this, I'm gonna do an underline here for subdivision of simplicial complexes. Yeah, yeah, that's true. But it's a different kind of subdivision. These are not equal. Okay, so before I have this functor sing, now I want to describe its left adjoint, realization. Okay, so I'm given a simplicial set and I want to get a simplicial complex out of it. So realization of a simplicial set is a simplicial complex. So I have the vertices are just the vertices of simplicial set, and x1 up to x0 up to xn is a simplex of the simplicial complex if and only if there exists an n simplex sigma in xn such that the ith vertex of sigma is xi. What does this mean? It means that I have n plus 1 distinct elements, and I have to have a simplex in my simplicial set with n plus 1 distinct vertices. That means it's non-degenerate. If you are a degenerate simplex, you cannot have all distinct vertices, okay? So that's this functor. And it has the nice property that if I take the subdivision osing of a ordered simplicial complex, so remember I have an ordered simplicial complex, I make it into a simplicial set, I subdivide it as a simplicial set, and then I realize it as a simplicial complex. That's the same thing as a subdivision of the simplicial complex. Now we have simplicial complex subdivision. Okay? All right. So this is basically what's going to give us the model structure. Okay? So if I want to transfer the model structure from simplicial sets, all I have to do is the following. Simplicial sets is a cofibrantly generated model category. So it has generating trivial cofibrations given by horns mapping into simplices. To transfer the model structure, all I need to do is show that, all right, so let me do it like this. I'm going to let tilde like this be subdivided twice. I have to apply this to J. I want to apply this to J. So I get something like this. And I want to show if I have a push out like this, then sing of this map is a weak equivalence. If I show this is a weak equivalence, then I've transferred the model structure. I have to prove a couple of other things, but those other things are automatic. This is the heart of the argument. Okay? So what actually happens here, I apply this thing to this. Well, both of these can be thought of as ordered simplicial complexes. I use this, and it turns out to just be, as a simplicial complex, that.
What was there before you erased it? 5 seconds ago?
I took this and I applied,
What was before you erased SB2? What was there before?
I applied RE tilde to this.
Was already tilde that, thank you.
I still have no intuition of why ST2 would work and the other one doesn't.
And I'm about to tell you.
Okay.
So now so there's two key results. There's this, and then there's the following fact proved by Matsushita. If I have an inclusion of simplicial complexes, if I have an inclusion, let's just write it like this, of simplicial complexes, then when I subdivide twice, I get an NDR pair. What's an NDR pair? An NDR pair is a kind of inclusion of simplicial complexes where there exists another simplicial complex in between like that, such that the neighborhood of K is inside L prime, and L prime deformation retracts
Del equals 0. That's exactly what I said before. Del is equal to 0. That's the same type of thing.
Sure.
You don't believe it.
So an NDR pair says I have a subcomplex sitting in between them, such that the neighbor, I didn't tell you what the neighborhood of K is, but you just imagine all the simplices that it touches, sit inside of L prime, and L prime deformation retracts to K. Deformation retract in the sense of that homotopy theory I talked about in the very beginning. Now, combining these two results, you can show that when you push this out, you get another NDR pair, and then you show that applying Sing to an NDR pair is a homotopy pushout. That gives you the model structure. Okay?
And you know, this subdividing, you get this nice property with the neighborhood.
You get a nice property with the neighborhoods. That's really homotopically useful. Okay? So, and this is also what Thomason does. This is like almost exactly the same thing in Thomason's paper, except it's much more complicated because he has to say it in a different way, and you also have to be careful about how the subcategories sit inside of each other. Okay, so you don't really see it quite as clearly until you get to simplicial complexes, and it's just an NDR pair. So for categories, it's like an NDR pair plus a couple of other conditions, okay? So maybe let me end here. By doing all of that, that lets you transfer to here, and then you can just keep transferring over. There's not a lot of hard math going on here, but there's one thing I do want to mention, which was for the Thomason model structure, remember that the fibrin cofibrin objects were really hard to get your hands on. Here we actually get a lot of cofibrin objects. Why is that? Well, this is a quill adjunction, right? So that means that this functor preserves cofibrations. It preserves cofibrin objects. So if I take a simplicial set, I subdivide it twice and realize it, I get a cofibrant simplicial complex. Okay, but what the hell does something in the image of this look like, right? Well, I can always do this. This is a simplicial set, and I can subdivide it twice and realize it, but by that result over there, it's just that. The second subdivision of every simplicial complex is cofibrant. Okay? And then from there, you can get more and more cofibrant objects.
Replace things.
Huh?
Very easy to replace.
Very easy to replace. I have a cofibrant replacement functor just by subdividing twice. I'll say one more thing.
You commutes.
Huh?
The composition commutes. You don't have that composition over here in this statement.
You don't have the composition
You
here.
have one subdivision. You don't have two of this isomorph in this.
Yeah, but I can just pass it.
That's what I.
Yeah.
Time.
Yeah.
Yeah, I'm using commute like for the days.
Right, right. And then the last thing I'll say is that I can prove that every complex that's cofibrant is in the image of CL. Okay? So everything that's, so I'll say, where CL, remember, is the clique complex functor. We call complexes in the image of this functor flag complexes, clique complexes, has like a ton of different names. Every simplicial complex that is cofibrant. So this is mirroring Thomason's proof that every cofibrant category is a poset. Okay? Okay, I think I'll stop there.
You're gonna get different homotopy categories there for each one of those. And I know
They're all quill and equivalent.
I know they're all quill and equivalent, but you should be able to say something about the homotopy. Forget about looking at equivalence of categories. Like some of them should be inclusions of others, of the homotopy categories.
All their homotopy categories are equivalent.
I know, but before you get to equivalence, are any of them inclusions of the others?
This one is. This one's, that's a fully faithful functor.
Homotopy categories.
And this one is fully faithful.
So that's the most rigid homotopy category, the GR. The homotopy category of that is the smallest one.
The category is the smallest.
Right, and so those are retractions to that thing.
Well, this is a reflective category, and this is a co-reflective.
And where does ordered simplicial sets fit in over here?
Order simplicial complexes like live here, and there's like a forgetful functor here, and a junction like this. And somebody else proved that this gives you another model structure.
But you also, right, and that's also equivalent?
They proved it's equivalent, yeah.
So
everything.
As always, Emilio, perfect.
Thanks.
Anybody have any more questions? We don't meet for another, I don't know, 3 or 4 weeks or something like that. I don't know. Anyways, we meet when the webpage tells us we meet.
Yeah. Well, we have Evan Mishula coming up next, right?